in the floor when I open the door for her. She acting like a whore and I'm a letter. Learn from Project Pat.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
We're going to discuss the day when we venture further in the solar system than our moon, and what does it take to get there. Here is a map of the solar system in terms of gravitational potential energy. So we are still going by this, what we learned. So that U is equal to minus G, whatever mass and whatever the mass of the central object, which in this case would be the mass of the sun. And that would be our distance from the center of the sun. So what do we have here? Okay, first of all, this is the zero level of potential energy. So wherever we are down here, we have the negative energies provided by this expression. So zero level here. And what you see here now are different planets. So from the left, you have Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. And how do you read this graph? So if we are here on the surface of the Earth, and to escape the pull, first of all, we need the 11.2 kilometers per second of speed to climb out of the Earth's gravitational well of its own. And once that has happened, we are under the influence of the sun. So to go from Earth to Mars, for example, the red planet here, we need a certain amount of energy. In fact, we have to speed up our spacecraft to get to a trajectory on Mars. And that takes about 4 kilometers per second additional. So you get the idea of the scale that we are talking about. So your rocket has to accelerate another 4 kilometers per second from Earth to go to a trajectory that will coincide with that of Mars. And the graph doesn't go in the way that you get a free ride if you go Venus. No, because if you want to go to Venus, which is closer to the sun, you have to brake your rockets, and you are expending fuel. So that's pretty close to the same 4 kilometers per second. What we also see that it doesn't take too much extra effort to get to the rest of the planets in the solar system. So for example, this level here would mean that we are in the vicinity of Jupiter. So that would be maybe just another extra 4 to get there. And then we could pretty much coast to Saturn, Uranus, Neptune, and escape the solar system altogether. The difficulty comes if we want to land on these planets. So what happens here? So the way to read this graph is once we get to the vicinity of Jupiter, we start in fact falling into its gravity well. But if we don't do anything, by orbital mechanics, we just bounce straight back like this. So we speed up and then slow down again. So if this is Jupiter, so we approach it at some velocity like this, we go close to it, maybe change the direction a little bit, and we speed up while we're close to it and then slow down as we get further away from it. The thing is, we are going fastest at the closest approach. That is, if we want to go to the surface, we would have to kill all this speed that we have gained under its gravitational pull. And that's, as you can see, is quite a bit in terms of kilometers per second. And in fact, this maneuver, where we exactly don't do anything, is known as flyby. So, as you know, the velocity is a vector quantity. So once we change the direction of our final velocity by this amount, some delta t or delta theta, what happens when we go back to the frame of reference of the Sun, it so happens that the speed of the spacecraft has indeed increased. So these massive planets, or any given planet for that matter, can be used up to speed up our spacecraft. And essentially what happens here is that the spacecraft picks a little bit of the kinetic energy of the planet, and the planet loses some. And somebody has made an estimate that all the flybys that the spacecraft have done so far, it has changed the orbit of Jupiter by 1 foot. I already talked about the relationship between Einstein's and Newton's mechanics, and here's an example of it. What you see in this picture is not just the potential well that we have discussed so far, but this is the Einstein's interpretation of time and space. So what he claimed was that the time and space are an interwoven fabric where one affects the another. So if we first think about the potential well analogy, that also applies. So here's the moon circling the Earth. So it cannot escape the moon because it cannot get up from this hole in the time-space fabric. But what also happens is that when objects are somewhere in the fabric, the time runs differently. You have come across with this idea of time dilation when the objects are going at fast speeds, for example, like the GPS satellites. And it's not only their speed, but it's also their location in the potential well. So once they, let's say they are circling Earth somewhere around here, they are further away from the, or they're in a different location on the time-space fabric than we on the surface of the Earth are. And in fact, the deeper we are in the well, the slower the time runs, according to Einstein's theory. So the satellites that are whistling further away, the time for them ticks faster. And in fact, for the GPS satellites, that is about 45 microseconds per day. And the other relativistic effect that they're going at high speeds reduces that time by 7 microseconds. So in total, we're talking about 38 microseconds per day. This means that without these relativistic corrections, the GPS system would be off by 10 kilometers per day. And what makes the Einstein's achievement so remarkable is that he came up with his new theory without any observations to support his claims. They only followed afterwards.
Money make a crowd go down.